Okay, so the last section in this chapter, last part of the chapter anyways, is something called Standard Enthalpies of Formation, and it's one of the more useful things that you learn out of this chapter. And so to start with, let's sort of define what a standard enthalpy of formation is. Standard enthalpy of formation is the formation of a compound from its reference elements. Okay, so for example, you can do the formation of these products from carbon solid, which is coal basically, hydrogen gas, and oxygen. And if you can calculate from these, or do the reaction from these substances to get the formation of this product, water, right? And you can also do the formation or the energy for the reaction of these reactants to these products. Then what you can do is similar to Hess's law, and this is in fact an application of Hess's law. If you know the energy from this state up here to here is minus 483, and this state from here to here is minus 393, you can calculate the energy that it takes to go from these reactants to these products. And so this is the idea of standard enthalpies of formation. They calculate the energy for the formation of substances from the elements that they're composed from. So we call those, again, standard enthalpies of formation. So I just stole this problem from the book. These are kind of fairly straightforward, but I'll have to show you some other information before you can maybe do these on your own. But we want to do the standard enthalpy of formation reaction for NO2. So that would be from nitrogen gas plus oxygen gas to form NO2 gas like this. And now here's the deal. How did I know it was nitrogen gas? How did I know it's oxygen gas? Because those are the forms of the elements you most likely are to find them in nature. They're diatomic gases, so we use their diatomic forms. Carbon is a solid. Iron, magnesium, all those would be solids. And so when you look at the periodic table, right, the states that you know, the ones which you know are all solids are typically solids. The ones that you know are gases are typically gases. The ones that are diatomics, their reference form is the diatomic molecule. Okay, so again, looking at a periodic, elements like lithium and beryllium, all the transition metals, are typically their reference form would, for example, be lithium solid or chromium solid, because these are all solids in their sort of natural form. And then these, like, again, carbon would be a solid in its reference form. So carbon solid. Nitrogen is one of the diatomics, so N2, O2, F2, Cl2, Br2. These would be all the diatomics, and Br2 would be a liquid in its reference form, because it's what form you would find it most stable at room temperature, that kind of stuff. I2 would be a solid, and then these guys are all gases as well in their reference form. So basically what you would expect to find them on the periodic table is what you expect their reference to form to be. Now, some elements form multiple species in nature. For example, oxygen. Can't get my pen to work. Hang on. Oxygen is either O2 or O3, right? This ozone. Usually, although not always, it's the most stable form. But in any case, one of them will be chosen as the reference form, and then all the energies will be calculated relative to that compound having an energy of 0, okay? Or that element having an energy of 0. So let's go back to this reaction. Now, this isn't quite the right reaction. I have to have it balanced, right? So to balance it, really goes like that. So I'll have 2 nitrogens, and then I'll have to have 2 oxygens. And this would be the balanced equation, but the reference equation is per mole of substance. And so this would be NO2 gas, and this would be O2 gas. And even though you're not supposed to do this, this would be 1/2 N2 gas. And this is the let's see, yeah. This is the equation for the formation of NO2 from its reference forms. Okay, so this is the standard enthalpy of formation reaction. So if I wanted to know how much energy this took to form, then what I have to do is I have to have a table. And the standard tables are actually in the back of your book in Appendix B. Okay. And then let me show you where you can find that real quick. So here we're at the Canvas site, and under the resources now I filed in Appendix 2, Tro 4th edition PDF. It's essentially the same as the 5th edition. And when you click on that, you'll see something that looks like, well, it'll open up to another window, and when you can open it or you can download the file to your computer. And we want to know the standard enthalpy of formation for NO2 gas. Right? So what we need to do is we need to sort of scroll down here. You notice it's alphabetical by element. Most likely nitrogen is what it's listed under, so I'm just going to keep scrolling down until I get to the ends. Did I pass it? No, I didn't. There it is. Nitrogen. And then I go down and find NO2, and it's right down here. Now you notice there's 3 values here, right? If you go to the top of this table, these are all the standard enthalpies of formation. So the energy to form NO2 from its reference elements is 33.2 kilojoules per mole of NO2. So back here, this is 33 plus 33.2 kilojoules. And the reason I didn't put the per mole here, like is on the heading of the table, is because for this reaction, there's 1 mole already present in the reaction. So this says, write an equation for the formation of each compound from its elements in their standard states. So this is the standard states, and it has to be balanced, right? And then we find delta H of the reaction in Appendix 2B. Okay, so let's take another one. Let's take magnesium carbonate. And then you go ahead and write what elements you think make it up. And then, pause the video. When you start, it'll have the answer worked out for you. So this is the equation written out. Basically, I just read this and I said, well, there's magnesium. I know that's a solid. There's carbon. I know that's a solid. We just talked about that one. And then I needed 3 oxygens. And I said to myself, well, how do you get 3 out of 2? So I just used a 3/2. So this is the reaction. And the next thing to do is find the delta H for this reaction, the standard enthalpy of formation. And that would be right here, magnesium carbonate. So it's minus 1095.8. 1095.8 kilojoules for that reaction as it's written. Okay, so how else? What else can we do with these numbers? So this next skill is one of the more important ones. It's being able to calculate the enthalpy of a reaction when not everything is in its reference forms. And the formula for it, just a basic idea anyways, is that the delta H of the reaction is equal to the delta H's of the products. And this is the way they usually write it. I'll show you how they usually write it. They go N summation delta H of formation for the products minus N summation delta H of formation for the reactants. I'll explain to you what those different symbols mean and how you use them with this equation. But basically, it's final state energy minus initial state energy. And what you do is you find the standard enthalpies of formation for each one of these, okay? And you calculate the energy of the products, taking into account the moles of each substance, and you do have to pay attention to states. And you calculate the energy of the reactants, again, taking into account the standard enthalpies of formation for each of the reactants times their moles, right? And then you just subtract, and that'll be the standard or the delta H of the reaction from the standard enthalpies or delta H's of formation. And I'll talk a little bit about what standard means. It doesn't really mean that much other than it's a definition, but you do need to pay attention to some of that stuff as you move along in the sciences. But having said that, let's go ahead and do this problem. So this is what I'm going to do. I'm going to write out what I'm looking for. I need to do delta H of the products. So this is my product side over here. And so I'm going to say 2 times the delta H of formation for water in its liquid state. And then I'm going to add to that 2 times the delta H of formation for SO2, sulfur dioxide. And then that'll be the energy of my products. And I'm going to subtract from that, so this is this part, 2 times the delta H of, and I'm going to put this all in parentheses, delta H of formation for my for H2S plus 3 times my delta H of formation for O2, like this. And then I'll subtract that. This gives me my delta H of the reaction. So again, products minus reactants. Now, make your life a little simpler. Look at the things that you have and check to see if any of them are reference forms, okay? So O2 gas is the reference form for O2 gas. And delta H of formation is the energy it takes to make the substance from its reference state. So basically, the delta H of formation for this reaction is this. How much energy does it take to do this? Right? And you should intuitively understand it shouldn't take any energy to make something from itself because it's already itself. So it turns out this one will be 0. Okay, and we'll look at that. We'll look at it on the table. So now what I'm going to do is I'm going to look up these values. Now often what I do when I do these problems is I actually go to the tables and I write them underneath each one of these chemical formulas so that I have them, and then I go ahead and do this next part like I'm doing now. But now we're going to go look them up. So I need to find H2O liquid. Now that'll probably be under hydrogen is my guess. But I could be wrong, right? Oh yeah, look at that, I was wrong. So what does that mean, right? It means it's listed under oxygen. It's not always the first element. So you got to scroll down to oxygen. There's H2O liquid, and it's minus 187 point. Oh, sorry, minus 241.8. No, minus 285.8. See, the states matter. So minus 285.8. So this is minus 285.8. And this is in kilojoules per mole. But what I'm going to do is I'm going to multiply that. Sorry, it's going to be kilojoules. I'm multiplying that by 2 moles, and so the mole units will cancel out. And then to that, I'm going to add 2 times that for SO2. And so now I'll go to sulfur, because I'm going to guess it's under sulfur. You can see this table is pretty big. So SO2 gas is minus 296.8. So this is minus, sorry, it's going to be 2 times, and then minus 296.8. And again, the units will be kilojoules because I canceled that first part out. And then I take this whole thing, and then I'm going to subtract for H2S. So I'm going to look for H2S, and there's H2S gas. There's also H2S aqueous, right? So let's make sure I have the right state. And it's H2S gas, because this is reactants, right? So all this stuff is over here. And so what do I have? I have minus 20.6. So it's going to be 2 times minus 20.6 kilojoules. Plus, and then we'll verify that O2 gas is 0, right? So now we got to go back to oxygen. I should have probably checked it earlier. You notice O2 gas is 0 because it is the reference form. So to form O2 gas from O2 gas takes no energy at all. Manganese, you can see a couple others here. Mercury liquid, things like that. Those are the reference forms. So I can put in a, 3 times 0 here, but that doesn't really matter because that's going to go away. And now I get to do the math. So I'll pull out my handy dandy calculator and just type the numbers in. So, and I'm doing this for a reason because there's a common mistake that people make, okay? So I'm going to go 2 times and then 285.8 negative plus 2 times 296.8 negative. I'm going to hit equals. And that becomes negative 1,165.2. And then I'm going to subtract my reactants off, right? And I think some of you probably already guessed what the common mistake is. This is going to be, though, minus 41.2 kilojoules, like that. So I got to do the subtraction. And then I'm going to say, well, 41 minus, right? And then 41.2, and then change sign like that. Oh, I screwed it up. Let's just redo it again. So 1165.2 change sign minus 41.2 change sign like that. And I get 1127. So negative 1127 kilojoules, like that. Okay, so what's the common mistake? It's this. You often skip one of the negatives, so you end up actually subtracting it, when in reality, the two negatives means you're actually adding the 41. So sort of double check, sort of to make sure, like, your numbers make sense, right? So this is minus 1165, and this is about 40 higher than that, so we're good. Okay, so that's the standard. So delta H of the reaction from the standard enthalpies of formation. So, and you can do this for basically just about any substance you can think of. It has a standard enthalpy of formation, and you can calculate how much energy it takes to produce that from other things. Now, one last thing I wanted to go over, and then I'm going to cover a little bit about standard conditions. This is actually from a homework problem, I believe. And they're actually asking you to calculate delta H of formation for CH3NO2. And actually what they do is they give you this energy, right? They say that's the heat of the reaction. So how do you calculate? They want you to calculate this value, or this substance's standard enthalpy of formation. And the way you do it is this. To start with, make your life easy. These ones are all 0. Okay. And then you go ahead and you do products minus reactants. So products minus reactants are going to be this. 2 times the value standard enthalpy of formation for CO2 gas, plus 3 times the standard enthalpy of formation for H2O liquid. So that's your products, and then you're going to subtract your reactants, right? So it's going to be, oops, sorry. Sorry, got all these slides mixed up here. It's going to be 2 times, right, the delta H of formation. Gosh, I don't know why my screen's doing this. Every time I touch it, it just jumps a bunch of slides. Of CH3NO2, like this, okay? And then and I got to do the H2O, so it's going to be plus 3 times this delta H formation, standard enthalpy of formation for H2O liquid, like that. And this is, oh no, that was it. Sorry, I got myself confused. I had it right the first time. That's going to be that, and that equals negative 1418 kilojoules, right? Okay, so delta H of reaction. So it turns out you can find this, and you can find this. So this is the value you're looking for instead of this. Normally we're looking for delta H of reaction at standard states, but you're given that value. So since you're given that value, you can solve for this value that's here. Okay, so that's just a different kind of problem, and I know it's a little bit confusing, so I sort of show it to you guys in the lecture. So last thing is just talk about standard conditions. Okay, the standard state in thermochemistry is the pressure as 1 atmosphere, and the concentration, if it's in a solution, is 1 molar. And one of the things that constantly trips up students and instructors is they think temperature is part of the standard state. It is true that there's a standard pressure and temperature, but it turns out there isn't a standard temperature that goes along with the standard state in thermochemistry. It's just pressures and concentrations of solution. So that's the only thing I really wanted to say about that. And then I did rewrite, like, this is a standard enthalpy formation. I actually had these slides in a slightly different order before, but I thought it went better the way I rearranged them. All right, so that's it. I do have one other little thing I'm going to leave at the end. I used to just do random problems. That's my little table I would use for random problems. I'm going to leave this problem here at the end. And it's just a fun problem to figure out, like, how much energy do you have, how far do you have to walk to burn off 3.4 calories. Remember, that's our M&M energy. And I'll just tell you the answer is close to 600 feet. So I'll leave this rest of this up to you to calculate. It's 596 feet. It's just a long and kind of an interesting conversion problem.